So initially I had this lesson broken into 2 lessons, but instead of being 2 lessons, I'm going to actually consider it as make this into 1 lesson, and then you're going to have kind of an exploration lab activity that goes along with it. So what we're going to be looking at is 2D kinematics. So we're looking at objects in free fall. Adjust my screens here. Objects in free fall and projectiles. So what is projectile motion? And your final assessment's actually going to work more with projectile motion. It's really good for giving explanations, and there's some really good trade-related examples that can come from it. So thinking about how it relates. So you're going to spend a couple days, the equivalent of a couple classes, just working on projectile motion. So first of all, what are projectiles? So projectiles are any object that have only the force of gravity causing their motion. So let's say you've thrown a ball. The minute that ball leaves your hand, gravity is the only thing impacting or causing its motion. Okay, you've set it in motion, but the change in motion. Another example, you drop a wrench. Gravity is the thing that's causing the change in motion. There's also so many examples we could have of that. If you had a bird get hit by a turbine and killed, is one example. If it can no longer fly, gravity is going to take over, and that it now becomes a projectile. So there's lots of examples of things we could consider to be projectiles. Now, most of the things in the real world are not what we would call true projectiles in physics, because in physics, a true projectile has no lift or drag from the air and no means of self-propulsion. Now, no self-propulsion is easy to control, but no lift or drag is impossible to achieve. So we're going to assume very little lift or drag, and we're going to work with a simulator that has lift and drag. We can kind of eliminate from it just to kind of investigate the principles a little bit better for us. And the other thing that's important with projectiles is they have to have a short path compared to the size of the Earth, and I don't think any of us are planning on hitting any home runs that are going to go more than halfway around the world or anything crazy high out of the atmosphere. So we don't really have to worry about that, but that is another definition of projectile, because if it had a really long path, if it was in the air long enough, technically the rotation of the Earth would also impact the kinematics, because the Earth is moving as well as the object. So things that we don't want to think about. So we're going to simplify, and for all of our projectiles, we're going to assume that only gravity is at play and that they all have short paths. So we don't have to worry about the rotation of the Earth or gravity changing, because at varying heights, the higher we go into the atmosphere, gravity can change. All right, so there's 4 different scenarios for projectiles that we're going to look at. One of them you've already done. We looked at it last class, and we didn't really think about it so much as a projectile. We didn't use that term, but we did this first scenario where somebody drops a ball and it follows a linear path, a one-dimensional path. So we could trace its motion with a single vertical line. And it only has motion in one direction, so it only has motion vertically. So that's an example that we looked at before, and that was also in your assessment, where something falls, how long does it take? And we find that gravity is equal to 9.81, so we can calculate how long it takes to fall and how far it's fallen. If we look at the second example here, and it's really hard to get a decent picture. I've edited the picture to make it show what I wanted it to show, but I'm not sure it has. So we have somebody throw a ball straight up in the air, and then the ball comes down to them. So again, we're perfectly vertical. Everything is staying in one direction. So those are going to be our easy examples to deal with, and they'll give us some of the fundamentals. Then we're going to look at, well, what if we're not just throwing straight up? What happens when I throw out and something falls? Or maybe we bat a ball up in the air and it follows the parabolic, that's the shape of that curved trajectory. So it goes up in the air and then comes back down. How do we handle those? Because it's going, not only is it moving vertically, but it's also moving horizontally. So we have motion in 2 directions. And as you can probably guess, we're going to deal with a little bit of vectors. So if I think this lesson is taking too long, I'll break it into 2 components for us. We'll definitely look at this one first, and I'll see if I need to I'll cut it into a second video to show you the other examples, but I think we can probably manage to do this all in one, and you can just make use of your pause button and come back to it if you need to. So first of all, this is a scenario we're quite used to. So the ball is thrown up into the air and comes back down. What do you notice about its speed as it rises and falls? You'll notice as the ball goes up into the air, the closer it gets to the top of the path, it appears to slow down, and then it picks up speed as it drops back down. So we can actually use this to help us out. So I'm going to make a few notes just on this image about what happens to an object once it's tossed, once it leaves my hand, only gravity is controlling it. What happens to the object and what do we see? So the first thing we have, the object moves up, and as it moves upward, it slows down. Okay, it slows down as it moves upward. That's because velocity is positive, but acceleration is negative, and they work against each other. So we have the highest velocity here. I'm going to call it highest speed here, only because it could be going up or down, and at that point, it will have the greatest speed if we ignore the signs on it. Then it's slightly slower as we get to the middle point, and as we get to the top, you ever notice you get that hang time? You just waiting for it to turn. That's because the velocity becomes zero at this point. So there's no speed, no velocity at that point. So for a moment, that ball stops. And I think the little graphic did a good job of simulating that for us. And then it changes direction. And after it changes direction, we find it moves downward. And as it goes downward, it speeds up. And why does it speed up? Well, velocity is negative because it's moving downward, and acceleration is negative because the acceleration due to gravity is, we can call it A, is negative 9.81 meters per second squared. It's always going to work downward. Sometimes we'll say G equals negative 9.81 meters per second squared. You're going to find we'll use G quite a bit when we get to kind of the next section of physics instead of using the letter A, but they can be used interchangeably. So for an object that's thrown vertically, as it moves upward, gravity is going to slow the object down until we get to a point where the velocity is zero. Once the velocity is zero, acceleration is going to keep making the velocity get more negative, and the ball is going to drop. Okay, those are really important concepts to know because it's going to help you with your calculations. If you understand those really simple pieces about what happens to a ball when I throw it in the air. Toss something up and down a couple times and just observe what happens. So when we solve 1D projectile problems, first of all, a dropped object or an object that is thrown straight up has no horizontal velocity. Now, right now you might say, why am I saying that? Well, I'm saying that because in the next section, we're going to change, okay? So no horizontal velocity, everything is in the vertical direction. Acceleration is always going to be 9.81 meters per second squared because it's coming from gravity. And if you throw an object straight up, the velocity just before the direction change will always be zero. Now, one other key piece that I should pop in here. When the velocity is zero at the top of the path, this is equal to half time. Okay? At half the amount of time the object has spent in the air, the velocity is equal to zero. And that's true of any symmetrical path as long as you're starting and ending at the same height. Now that's going to be really helpful for the example that I've given you to solve. All right, so we're going to use all the same equations as before, so we don't really have any new math. We just have a couple new concepts, and it's going to involve putting multiple pieces together. I'll confess, this is the more complicated section. So the lab activity, I hope, working through it will be like working through a couple of quizzes and give you the ability to have a better understanding. All right, so let's start with an example. A ball is tossed straight up into the air with an initial velocity of 15 meters per second. So you should have a visual of that from the previous slide. Assuming air resistance is negligible, so that's telling me it's a projectile, how long will the ball be in the air before it is caught again? Okay, so we want to know time. So we can, first of all, let's list our pieces of information just like we would in one of our other questions. So the ball's tossed straight up into the air with initial velocity of 15 meters per second. So that's our V naught, 15 meters per second. And we know our acceleration, they're told it's projectile. So, well, we're not told it's projectile, but there's enough information to solve that. So acceleration is negative 9.81 meters per second squared. And then we don't know time. So we'd like to find time. But that means we need one other piece of information. And what other piece of information do we have or could we have? So let's think about this ball as it goes up in the air. So I'm going to draw it like I'm going to do what I call a velocity time graph. So here's the speed of the ball and this is time. So you throw it up into the air and as it goes up into, never mind that. It's not the path that I want to do. I'll have to draw, it's going to be less intuitive if I draw it that way. Ignore me. I'm going to sketch it the way I normally would. So you're throwing a ball up in the air. The ball goes upwards. And as it goes upwards, it's not moving as fast. We'll say our dots get closer together. So the ball goes up and then it goes down. Now we know at the top of the path, velocity is equal to 0. And this is time, I'll call it T1 half time. Okay, so the velocity at the half time is equal to 0. Will that help us out? There's another piece of it, so we can use that to help us out. There's another piece of information you can think about. So that was given in your last slide. Velocity at the half time is equal to 0. So we could figure out, well, how long does it take to get to 0 and then double it? The other thing about a projectile is they're symmetrical. So as gravity pulls on that ball, it slows it down, moving upward the same amount as it speeds it up going downward. That makes sense? So the amount it slows down on the way up is equal to the amount it speeds up on its way back down. So because they're symmetrical, we can say our final velocity, so the velocity at the ending, so velocity here is equal to positive 15 meters per second. We can say the velocity here is equal to negative 15 meters per second. Both are true. So now we have two different ways we could solve this problem. We can solve this problem by breaking it into two. We can say, well, how long does it take to get to 0? And then double that. Or you can say, well, I know velocity going up was 15 meters per second at the start. And at the end, our final velocity, I'll call this V naught, our final velocity over here is just in the opposite direction. How do we calculate it? So it's really quite easy. So we'll go with this version. I did do the halftime, and it's funny because sometimes that's the challenge about these questions. Sometimes you look at it, and one time you look at it, you see, oh, well, I could solve it this way. And another time you look at it, you go, well, why didn't I see that I could solve it this way too? So that's just, it doesn't matter how many of them you do, that happens all of the time. At least it happens to me, so I don't know about anybody else. So now we need to find an equation that uses time, acceleration, and two velocities. And if you look here, our first equation here has final velocity, initial velocity, acceleration, and time. So let's use that one. We'll plug in and solve. Velocity equals V naught plus AT. So at the end, when it's dropping, it's going negative 15 meters per second when it comes back to my hand. When it left my hand, it was going positive 15 meters per second. Plus we had our acceleration of negative 9.81. And I like to leave that in brackets just because of that negative sign. I just don't like seeing positive and negative sign next to each other. It messes with my head a little bit. So now that we have all this, we can solve. So these are multiplied. We can't do anything with it. So we're going to move the 15 first. We're going to subtract the 15 to the other side. Again, we're doing some algebra. So negative 15, take away 15, we got negative 30. Become more negative. Those ones cancel out. Equals negative 9.81 times t. Dividing both sides by negative 9.81. How long do you get for time? So 30, negative 30 divided by negative 9.81 leaves me with 3.05 seconds. That's how long the ball was in the air. Now, if you did it calculating halftime, I'm just to tell you, if you did it calculating it with your halftime, I have exactly the same answer. I have three seconds there as well. I have 3.05 seconds here, but really I should do 2 digits because of this 15. So you could say 3.1 seconds, but that's exactly what I calculated too using. So there's more than one way to solve these, and that is perfectly acceptable. Excuse me. All right. If you have questions about that, let me know. I think as you do some more questions and even as you kind of play around with things in the simulator, you'll discover, or you'll see some of the concepts may be solidified for you. All right, so that's the only example question I'm really going to do with that. And then we're going to get into, well, what happens when we have 2D motion? Because we're going to repeat the 1D results with our 2D motion. So normally, if you launched an object horizontally, if there was no gravity, the cannonball would follow this horizontal path if there was no gravity. But because there is gravity, the gravity pulls the object downward. Now, the question I've presented on this slide is, does the presence of gravity change the horizontal motion? In other words, is there any horizontal acceleration or deceleration? Is there a change in horizontal speed because of gravity? Think carefully about that, and I want you to think about which direction does gravity change the motion of? You'll have the answer within 2 slides. Okay, so now I want you to think. I know people don't really like to think, but I want you to think. Suppose a rescue plane drops a relief package while it's moving with a constant horizontal speed at an elevated height. So we've got our lovely little guy flying. He's got his little box there. Assuming that air resistance is negligible, so we're assuming perfect conditions. We're also assuming there's no wind. Another important piece of information. Where will the package land relative to the plane? Will it land behind the plane? Will it land under the plane, or will it land ahead of the plane? What do you think will happen? And why? I'd love to throw this in a discussion forum, but I want to give you the answer right away. So hopefully you've got your answer, and I'm going to show you a GIF that answers this. I apologize, it kind of repeats over and over and over, and then we'll look at it still in a minute. So we have our lovely plane flying across, it drops its parcel, and notice when the plane gets to the end, notice the parcel, the little red ball, and the plane. See how they continue exactly together. The plane is not being affected by gravity, but the falling package is. So, to go back to the last question, where did the box land? Well, the box landed right under the plane because the box was moving at the same speed as the plane until the plane dropped it, but it kept moving horizontally at that speed. The only issue is gravity pulled it down to the ground. So, to pop back to this one, does the presence of gravity change the horizontal motion? Well, you saw on the plane, as the plane flies across, as the plane flies, the parcel stayed lined up directly underneath of it. So if we could have ignored gravity and just looked vertically, they would have stayed in line. That tells me that the presence of gravity does not change horizontal motion. Gravity only impacts the vertical direction. So when we're dealing with projectiles in 2 dimensions that are moving both horizontally and down or vertically, we're going to have to think about the question separately, because in the horizontal direction, there's no gravity, because we just saw gravity doesn't impact it. But in the vertical direction, we find that, yeah, gravity definitely has an effect there. Well, what's the vector direction of the acceleration due to gravity? It's downward, it's in the vertical direction. So it makes sense that it's only going to affect the vertical speed of an object and not the horizontal. All right. I guess I didn't have to jump all the way back to that. Sometimes I forget which slide I put next. Another think question. If the horizontal and vertical motion of an object have to be analyzed separately, is there anything between the two that would have to be the same? And what I'm thinking about is I'm thinking about the variables that we use. So we know that velocity is different. So velocity is different, and the starting velocities could be different for horizontal and they could be for vertical. It's often the case. Distance. Is it the same between the two? Well, this cannon might land at the same distance out as it dropped, but not necessarily. If I'm throwing something, I can usually achieve more height than horizontal distance. I'm not exactly your best arm. So distance and height, they're not necessarily, like horizontal distance and vertical distance, they're not necessarily the same because they're in 2 different directions. So they're often different. What about acceleration? Well, gravity only works down. If there's nothing else pushing it, it doesn't have any horizontal acceleration. So acceleration is different. What's the only thing I'm missing? If you said I'm missing time, you're correct. Let's think about time. The time it takes this cannonball to drop, to land here, the time it takes for the cannonball to descend, and the time it takes for it to travel horizontally, will they be different or the same? They have to be the same. If they weren't the same, an object could be in one place, it's like being in 2 places at one time. That wouldn't work. They have to stay connected. Okay? So the time for an object to fall has to be the same time that it takes for it to travel horizontally. So time is always the piece in our puzzle that will be the same between horizontal and vertical. Okay? That's going to be really important for us to remember, because it's going to help with our calculation. So time is always the missing link between how far something goes horizontally and how long it takes to drop. Because my landing spot here is really dependent on how long it takes gravity to pull it to the ground. Once it touches the ground, horizontal motion can't happen anymore. I mean, it may roll a little bit, but we're done with projectiles now because now it's on the ground. So this time, the time to drop has to be the same as the time that it was in the air going horizontally. It's really an easy concept, but for some reason, it messes with people a little bit sometimes. So if you need to talk it through, find a friend, ask some questions about it, or pop me a message and meet up with me. I'm more than happy to discuss. And it's always good to just kind of think about some examples. All right, so what do we do when we solve 2D projectile problems? Well, I don't really like this slide, but that's okay. I've changed it enough times, it's staying as it is. First of all, sort the information into X and Y components. So I want you to take the information in the question and we're going to categorize it by what is vertical motion and what's horizontal motion, because it's going to give us two different scenarios. Secondly, we're going to solve for time. Most of the time is what you want to get first. It's the key that links both X and Y together. So if you haven't calculated time in the question, you probably haven't finished the question yet. And lastly, then we're going to analyze the horizontal and vertical motion separately to find final velocities, distances, etc. But time is always our missing link. An important thing to notice, horizontal will always have constant velocity. I have equations on the next slide that'll give us our constant velocity equation. Constant velocity means acceleration is equal to 0. So that means velocity is equal to distance divided by time. That's only for horizontal. In the vertical direction, we always have acceleration due to gravity, which is going to be negative 9.81. All right, so let's go through a couple questions. I'm going to get rid of my video here because we're going to need some more screen. And we're going to go through a couple questions and we're going to figure out how do we solve it. I'm going to go through two questions and two different types of questions, and then you're going to do some exploration in a lab. And I'm not going to give you a second lesson on this. The lab will serve as your second lesson because I think it's scaffolded in a way that will give you all of the practice that you need for these pieces. And it'll also tell me what you really know. So to start off this question, we'll read it carefully and see what information we can extract. A rock is thrown parallel to the ground at a speed of 10 meters per second from a height of 6 meters. How far will the rock fly before hitting the ground? B, what will the resultant velocity of the rock be as it hits the ground? Now, resultant velocity should make you think back and go, oh crap, do I remember vectors from last semester? But before we get there, let's get A calculated first, okay? So let's calculate A. And while we're calculating that, I'm going to go find my solutions for this because it's always helpful if I have my worked out notes as well. Okay, so hopefully you've had a chance to start categorizing the information. So I'm going to categorize information by X and Y. So in X, I have acceleration equals 0. That's horizontal. I told you that before. Oops. Yeah. So here's our picture. We've got the top of our cliff, let's say, and we're going to throw a rock in this direction, and it's going to come out and it's going to land down here somewhere. And we want to know what's this distance. Okay? So acceleration horizontally is always going to be 0. Velocity horizontally isn't changing, so there's only going to be one v there, and it's our 10 meters per second. Okay? And so acceleration, velocity, and time, we don't know. We also don't know distance. And that's all the information that we can have in that side. So you'll notice we're missing two pieces of information. That means we cannot solve anything using this X. So we're going to have to find some other information out first. Why? Let's list our pieces. We know acceleration is equal to negative 9.81 meters per second squared because we're dealing with gravity. Now, is the velocity changing? So as we throw a rock horizontally, the second it leaves your hand, if you gave it only horizontal, so parallel to the ground, only horizontal speed, it starts out with a vertical speed of 0 because you haven't thrown downward, you've thrown horizontal. So that's one of the little tricky pieces. So velocity at the beginning, the downward velocity is going to be equal to 0. Now in the simulator, I'd like you to select vector mode at some point and take a look at this and see how does that work so you can remember it. So the starting velocity when we throw something horizontally will typically be 0 for the y direction. The final velocity in the y direction, we don't know, we're not given it. The distance in the y direction is equal to, we said, oh, just 6 meters. So it's height of 6 meters, so that's our 6. And then we don't know time. So now we need to look at our question. We're missing 2 pieces of information here, but there's still not enough for us to solve this question because the only equation we have for x direction is this one. This is our x equation. It uses velocity, distance, and time. And we're missing 2 of the 3 pieces, which means we cannot calculate this piece yet. Secondly, okay, even though we're going to need that to find out how far. So the first thing we're going to find, like I said before, we're going to find the thing that links the x and the y together because we usually will need that to solve. So we're going to find time. So how long was this in the air? Well, we have an acceleration, an initial velocity, and a distance. Which equation uses acceleration, initial velocity, and distance to find time? Well, we're going to use this equation here. Distance is equal to v naught t, initial velocity times time, plus 1/2 at squared. We'll substitute our information in. So 6 is equal to initial velocity of 0 times t plus half negative 9.81. Throw brackets around that just so I keep my negative. T squared. Now, normally I don't like this equation for calculating time. I will usually avoid it. But in this case, we get 0 times time, so that goes away. It cancels out, goes to a 0. So we're left with 6 is equal to half negative 9.81 t squared. So 6 equals negative 4.905 t squared, dividing both sides. That's what we end up with. Dividing both sides by negative 4.905, we get that, and we find that t squared is equal to 6 divided by, oops, it should be a negative 6. Sorry, I left that out. It was falling, so the distance was a negative 6, and I left that out in my notes, and I didn't put it in here, so I'm just going to go back and put that in. So I'll tell you what jogged my memory that I left that negative sign out. I will never get a negative time. So if you get a negative time, double check and see was something fallen. Easy spot to miss a negative. So negative 6 divided by negative 4.905 leaves us with a time equal to t squared equal to 1.22. And then you take the square root. And the time is equal to 1.11 seconds. And we had 3 sig figs, so we'll leave 3 sig figs. Now that we have that, we can go back and fill that in. 1.11 seconds. And it's going to be the same here. 1.11 seconds. So A says, how far will the rock go? Well, the distance that the rock goes this way is an x distance, horizontal distance. So we are going to use the x for how far. Think of y as how high. So I'm terrible for thinking something and writing down what my brain's thinking of the next step. X is how far and y is how high. So that can give you a couple pieces to think about. So we're going to use this information to find distance. Now there's a couple equations you could use. You could use the equation that we just used. Distance is initial velocity, or velocity times time, plus half at squared. Because you know acceleration is 0, so this is going to go away, or you can think about this equation. Usually I use this one because we know acceleration is 0. So how far, when we know velocity equals distance over time, so distance is going to be equal velocity times time, which is equal to, again, only use your x values. So we get 10 meters per second times 11.1 seconds equals 100. And sorry, I've got a number dyslexia here. Let's get rid of, instead of 11.1, let's do 1.1. 1.11 seconds times 10 would give us 11.1 meters out. Okay, so that's 11.1 meters. So relatively straightforward. Feels like a bit of a long question. If it feels like a long question, completely understandable. It is a little bit of a longer question. So now that we have that, I'm going to keep this information the same, but I am going to get rid of some of this to figure out the second part of this question. All right, so we're just going to erase a little bit. Hopefully you've got a chance to get that. If you didn't, just throw the pause on for a second. I think I probably go slow enough most of the time for you to get all the information recorded that you might need to record. Some of you probably wish that it went a little faster. My apologies, but it only takes so long to do questions. All right. And they need an easy feature for clearing a large section while keeping some questions, one part of the page live. All right, now we're ready for our second part. So we answered A, now we're going to answer B. What will the resultant velocity of the rock be as it hits the ground? So as it comes down to the ground, it has a velocity downward, plus it still has a velocity outward. So I want to know when it hits, what is the resultant? So in order to find the resultant, I need to know the final velocity in the x and y direction. So we'll make a list. So I need the final velocities. Final velocity in the x direction is going to be 10 meters per second. Why? Well, we just said in the horizontal, there's no acceleration. It stays 10 meters per second all the time. So we don't have to calculate it. But velocity in the y direction, I don't know and I need to calculate it. So how am I going to calculate that? Well, I would use this equation here. We have our time, we know acceleration, and we know what fast it was going at the beginning. So in the y direction, velocity in the y direction is going to be equal to v naught in the y direction plus acceleration in the y direction times time. So vy will be equal to 0 plus negative 9.81 times 1.11 seconds. All right, plugging that into your calculator. If you put that into your calculator, I believe you will find you get negative 10.97. I'm going to plug them into my calculator again, just because every once in a while I seem to have an error show up. .8, yeah, I'm getting the same numbers. That's always good. So I'm getting negative 10.89 seconds, or meters per second rather, meters per second. Okay. So we're going to take that and we're going to plug it over here. Negative 10.89 meters per second. Now to find a resultant, remember back from first semester, draw your x. So we're going to go 10 meters per second positive. We're going to go down 10.89 meters per second. And the resultant, this is the velocity that you actually feel if you were to catch or get hit by this. The velocity of the resultant is going to be the diagonal. Now you know your a squared plus b squared equals c squared. So the velocity squared is going to be equal to 10 squared plus 10.89 squared. And you can leave the negative sign out when you're putting it into Pythagorean theorem. That's fine. And it gives us velocity squared equals 218.6. Take the square root. And we get the velocity is equal to 14.8 seconds, meters per second. And then we need to know, so that's our resultant velocity. And the other piece we need to know is we need to know the direction. So if we want to know the direction, there's my angle, and we'll do just a quick calculation with it. So we're going to use tan. So the tan of our angle is opposite, so negative 10.89 over 10. So you get 1.089, and then you do the shift tan. So your angle is equal to the shift tan, so tan minus 1, do that shift tan of 1.089, and that's going to give us 47. Negative, it should be a negative 47. Yeah, negative 47 degrees. So it's at negative 47 degrees, or we could say 312, 313. Okay, so the resultant vector thing is a little bit tricky, might be a little bit long for you to try remember, but hopefully that isn't too bad for you. And we're down, oops, I did leave an extra slide for calculating that. We'll leave that for now. One last question to calculate, and then you're going to be free. A football is thrown from the ground with an initial speed of 25.0 meters per second at an angle of 32 degrees from the ground. How far will the ball fly before hitting the ground, and what will the maximum height, what will be the maximum height reached by the ball? So for a picture, you've got this ball and it's being kicked at 32 degrees and it's going to make an arc shape, specifically a parabola shape. How far will the ball fly before hitting the ground? So again, we're looking for a how far. So we want to know what is x, and then what will the maximum height, what will be the maximum height reached by the ball? So the other thing we want to know is what is y. So we have two pieces to solve. First things first, we have an angle in this question. An angle in the question tells me that I need to find my velocity and components. So I'm being told that this ball is being kicked at 25 meters per second, and that this angle is 32, and I need to find out, I need to know what's the y speed, because it has a velocity upward when it leaves the hand or the foot, whatever. And it also has a velocity along the horizontal because we want it to move down the field. So we need to find out what is Vx and what is Vy. This should take you back to your trig. So Vx is equal to, do you remember back in your trig? I'm going to actually erase, I'm going to write it out the long way just for a refresher. So back when you did your trig and you were trying to figure out one of the missing sides, X is adjacent to 32 degrees and 25 is our hypotenuse. So it's SOHCAHTOA. Okay. X is going to use cosine. So cosine of our angle is equal to opposite over, whoops, adjacent, sorry, divided by hypotenuse. So if I want to find the adjacent side is going to be equal to the cosine of the angle times the hypotenuse, which in this case is cosine of, I'm going to just change the way I'm writing that a tad. I'm trying to think of people who might get lost if you're not asleep yet. So velocity in the x direction is equal to the cosine of 32 times, and our hypotenuse was 25. Putting that into your calculator, you should get an x velocity equal to 21.2 meters per second. We're going to do exactly the same thing, but we're going to do this with the y velocity. So to get the y, it's opposite, so we're going to use sine. So sine of our angle is equal to opposite over hypotenuse. So we find the opposite is equal to the sine of the angle times the hypotenuse. So that leaves us with our velocity in the y direction. Oops, this is supposed to, I'm forgetting my letters. Let's just turn that back to an O. It's an opposite, not a theta. Velocity in the y direction is equal to the sine of 32 times 25, which left me with a velocity in the y direction equal to, in the y direction, 13.2 meters per second. Okay, so that means that it has a horizontal speed and a vertical speed. So this is the complicated kind of question, but you just did the hard part. That's the hard part already done. So what we do now is we do the same thing as we did before. We're going to categorize the information. We're going to categorize our x's and our y's so we can calculate. We might run out of space, but that's okay. We can erase and hopefully have a piece of loose leaf, or you can use another piece of paper. So in the x direction, horizontally, there's no acceleration. So we only have velocity, distance, and time. So in the x direction, it was kicked at 21.2 meters per second. Okay, the distance down the field, we don't know. We also don't know how long it was in the air moving down the field. In the y direction, we know the speed changes because gravity affects it. So the velocity at the start in the y direction is equal to 13.2 meters per second. Final velocity in the y direction, we don't know. But we do know some other information. We know the distance is something, we know acceleration, that's what I was looking for, is negative 9.81 meters per second. And then time is what we want to solve for. Okay? So this question has several ways that we could solve it. How we solve it isn't really going to matter, and you could actually solve B before you solve A if you wanted to. Okay, because B is looking for distance to the maximum height. How far will a ball fly before hitting the ground? So let's think. It feels like there's not enough information given. What is some hidden information that we've learned about projectiles? Let's label it. We know two things about projectiles. Projectiles that are symmetrical at the peak where they change velocity, it's a change direction, velocity in the y direction is equal to 0 up at the peak. Okay? The other thing we know is if it's symmetrical, the velocity in the y at the beginning equals the velocity in the y at the end, but it's going to be negative. So we have two ways we could solve this. If I kicked it with a speed or a velocity of 13.2 meters per second upward, when it comes down at the other end, it's going to have negative 13.2. And that's because it's symmetrical. Okay, so we have symmetry. Now we have enough information that we can solve. So now that we have that, we can find out how long is it going to be in the air, and that will tell me how far is it going to go. So how long is it going to be in the air? Let's use this equation here. Velocity, negative 13.2 is equal to positive 13.2 plus negative 9.81 times t. We're going to subtract 13.2 from each side. We're going to cancel out, and we're going to be left with 26.4 negative equals negative 9.81 t. Dividing both by 9.81, we get t is equal to 26.4 divided by 9.81. Whoops. 2.69 seconds. I always love it when I get a different calculation when I calculate the second time. That's never a good sign. So 26.4 divided by negative 9.81 leaves me with 2.69 seconds that it's in the air. And then if it's in the air for that long, in order to find out how far is in the x, we're going to take our bx times our time, which is equal to, we had an x velocity of 21.2 times 2.69 equals 57 meters. Okay, so what's the answer for A? A little complicated, a little bit ugly, but overall, not too bad. All right. Now I wish I had left a little more space, or I could scroll down to get a little more space, but I'm going to have to do a little bit of erasing here. And then we're going to figure out the B part of the question. What's the maximum height? So we'll just erase a little bit of the question. We don't actually have to have any of that information. And if you get a different number, please let me know. Just because I did have one solution key, and I'm not sure if I just hit a button in my calculator and didn't notice, but I did double check because I was calculating along with, and I have two different numbers. So if you get something else different, please let me know, and I'm going to check it again after I finish getting this put together. And all right, final one for B. B says, what will the maximum height be of the ball reach? So how high will the ball go? Well, at the highest point, the final velocity in the y direction is 0. So given that, we can say at halfway, we know velocity equals 0. The initial velocity is still going to be 13.2. So initial velocity 13.2, velocity is 0. We know acceleration is still negative 9.81, and we know that we want to find distance. Okay, so find which equation uses all of those, and the best equation for that, I think, could use a couple of them. Just in case the time is calculated incorrectly, we'll use this one. Doesn't use time. So velocity squared equals v naught squared plus 2ad. So velocity at the end was 0, so 0 squared equals v naught, it's just initial velocity, so 13.2 plus 2 times negative 9.81 times the distance. So that's our distance in the y direction. 0 is going to be 0, so we're going to get negative 13.2 squared. I'm not sure if that's the best way to write it. If you're slightly confused, maybe if you're slightly confused, I'm better off to go 13.2 squared equals 174.24. Moving things over, minus 174.24, minus 174.24, and then we're going to get negative 174.24 equals negative, be the minus, 19.62d, and then we're going to divide both sides. I'm going to just take this. Hopefully you can follow my arrows. Excuse my lack of spatial reasoning here. So we get negative 174.24 minus 19.62d equals negative 19.62d. Divide by 19.62. Divide by 19.62, and you get a distance of 8.8 meters. Okay, so that gives us our distance. Okay, so I apologize, it's maybe a little bit messy. What I'll do is I'll see if I can write it out using a little bit more of a linear fashion in maybe a Word document for you to help you out if you need the extra support there. But I think you'll find as you work through the simulation, it's going to answer any questions that you might be left with. So what I'd suggest is work through the simulation and come back to the questions if you need some help working through them. Again, I apologize for not giving you quite enough space to work on.